Thank you very much, and thank you for giving me the chance to present such kind of conference. Thank you very much. And my title is development of the high precision tsunami run-up calculation method coupled with the structure analysis, maybe by using the AWS. So I would like to talk. I would like to talk about the possibility of the AWS cloud computer. I'm not good at English, but so I want the innovative translation tools. If I say that I threw the mic the Japanese, then to change the Korean language or English, it is better. So I want develop the AWS company to such kind of tools. That is a very innovative ones. And but today I'd like to talk about the simulator by using the AWS. I know the tsunami event in 2011. Did you know that? But this kind of tsunami event is not only inundated but also the destruction against the tsunamis. So I would like to simulate such kind of destruction phenomena by using the simulators. So it is Onagawa town in one of the Tohoku district, one of the town of the Tohoku districts, and this is the inundation and the destruction of the tsunamis. So now the starting for the inundation. The inundated the flow depth is flow depth gradually little larger little by little. At first, of course, this kind of water is inundated, but then now these kind of structures, houses and the buildings, concrete buildings also were washed away by the tsunamis. And the height of the tsunami was 19 meters, so 19 meters here, and almost houses and buildings were washed away by the tsunami. So this is not only the water just only the water inundated, but the destruction against the tsunamis. And now the people who evacuated the roof of the buildings, there is some peoples. I think you can see the people who evacuated the roof of the buildings, and but no escape places against the tsunami. Then, but still, the water is growing up, and finally they are washed away. Everybody washed away, and they are not still they are missing. In this this area, I think the 10 seconds or 20 seconds they are missing. So these kind of I think that this is the tsunami disaster. Not only the water. Not only the water, but also the life. Yes, now everybody washed away. Only except for one people. But I think he was also washed away. So such kind of the disaster, if I want to evaluate such kind of disaster, so I want the develop the tools how to evaluate such kind of disasters. So now we will develop such kind of simulators, the connecting, so the multi-scale and the multi-physics tsunami simulators. the propagation. So here is a propagation. Propagation is the epicenter from the epicenter to the coast, and this is an inundation by using the Navier-Stokes equations. And these are connected with the structure analysis by using the FEM method. So this kind of simulator is very heavy simulations, computational from the computational viewpoint. So, so how to use the AWS? I will introduce. So at first, I talk about the multi-scale analysis. So a couple with the wave propagation simulations. From epicenter to these simulations, three different type of simulator is connected. The first is this is the name of Stockholm. The name is the name is not important, but this is a very light computational for the computational efficiency is very light. So that these simulations, the role of these simulations is to simulate from the epicenter to the coast. And in the coastal area, the more heavy simulations what is used. And the last one, inundation area, this is a very heavily simulations by using the three-dimensional Navier-Stokes equations. So these are the very these simulator connected with the connected with each other. So I would like to use the very large computational system. And this is not so important, but how to connect each other. So if you want, please tell me. I will tell you at very detail. But each simulation is connected by using the MPI library. So this is very normal way to connect each other. And I will show you about the accuracy of this computational methodology. So this is a town of the Onagawa. This is a town of the Onagawa. That is shown in the video. So from the epicenter is here over there. So from the epicenter to the coast this is a stock ML. This is a very light computation load. But the crossing the coastal area. Here is the red domain. I use the Navier-Stokes equation to evaluate the destruction phenomena. So this is one of the sample of the simulations in the Onagawa town, but this is not without the destruction simulations, just like that. Water. So I think that this is not so impressive for you, but the video is so impressive for you. But these are the simulations. The accuracy of the simulation is very good. I will show you. This is a comparison of the observation data. The blue one is observation data. The red one is the calculation results. And here is the Onagawa town, the map of the Onagawa town. And the blue one is the observation point and the observation data. And the red one is a calculation. So the average, from the average point of view, I think this calculation is it is very good. And this is a comparison with the time series of the flow depths and the flow velocity. Here is a point from the analysis point from the video, and this axis shows the time, and this vertical axis shows the flow depths and the flow velocity. And the black one is the observation data from the video analysis. And these orange one or something like the white one and red one is these are the model of the epicenter, the difference of the model of the epicenter. So I think this time series is very good agreement with good agreement with the observation data. So how to use the AWS simulations? Is it cheap or expensive? Such kind of simulations. At first, the characteristics of these kind of simulations. So I show you that this stock ML and the Cadmus stuff is the stock ML is a lighter computational efficiency, and these are the heavy computational load. So the blue one is a computational time, and the red one is a waiting time. So of course the waiting time is very large for the light simulators. So the improvement of our system improvement of the Cadmus South system, then the waiting time is a little bit small, and then I use the more so that this is the more CPUs, more nodes. Then every simulations there is no waiting time. So such kind of consideration is very important. So if this kind of load balance is very good enough, then I think maybe if we calculate 1 hour's calculations for the physical time, then it takes 10 to 20 days by using the AWS computer. Is it? I think it is very consistent by using such kind of cloud computers. And also, we are trying. This is not the AWS result, but also the K computer in the Japanese supercomputer results. So I try the 12 billion the total number of grid is 12 billions. So that means almost 40 gigabyte on the memories. Then then 9,000 nodes. If we use the 9,000 nodes, then the almost same computational time by using the 9 nodes computational case. So that means the huge cloud computer is has a very good possibility to calculate such kind of large simulations. I will cut this one. And proportional characteristics of the AWS I will show you. So this axis, sorry, I cannot see. Okay, this axis shows the CPUs, how many CPUs, so the number of CPUs. And this axis shows the ratio of the calculation time. So if this is a 9 nodes, so the 9 thread is 9 cores, and this is 1 instance and 2 instance. We use the C3 8X large. Is it okay? Okay. We are using the C3 8X large. I think this is maybe the best. Not best, but a better instance for using. And these are the 1 instance and the 2 instance. So the maybe four instance, the network time is waiting time is a little bit large. So I think if you use the 10 million grids, 10 million grid, that means for just 0.4 gigabyte memories, then I think such kind of result is the proportional characteristics. And we are checking the 100 millions. So 100 millions, if we use the 100 millions, that means 4 gigabyte memories. The memory overflow was occurred by using the 1 or 2 instances. So we are checking just 4 instances and 8 instances and 16 instances. So this is the cores and this is the time ratio. So maybe a little bit saturation will be occurred by using such kind of large calculations. So this is the cost of the calculation. That this is the money. So yes. So this axis shows the threads and this axis shows the money. So even if if in case we using the 10 million grids, then maybe two instance or 1 instance is very effective to calculate such kind of simulations. And yes, and almost $5 when the total number of grid is 10 millions for the 1 second physical times. So if we calculate 30 seconds or 1 minute, then the 60 times as the $5. That means $300. $300 is very cheap or not? I don't think so, but I don't know. But I think this kind of cost is needed to use the AWS. And this is for the K computer. For K computer is the Japanese supercomputer, and these are very proportional to the thread and the computational time ratio. So if you use the AWS, such kind of saturation will be occurred, but the K computer is a little bit proportional way. But I think so we are using if we use the total number of grid is very large, we will use such kind of simulators. So I think this is one of the summary of how to use the AWS. So maybe for our computers, for our simulations, such kind of Navier-Stokes equations or something like that, for the research, we are using the 1 or 2 instances better to calculation from the calculation efficiency point. And the relation between the accuracy and the grid size has been verified. So the cost for some accuracy will be shown by AWS using the AWS near futures. So then I think we are using the practical use by using the AWS for the research. So these are the future research, how to destroy such kind of simulations, how to destroy against the tsunamis. These are the cross section between the breakwaters for the breakwaters before and after. After is a red one, and the before is a black one. So that these kind of breakwater was washed away by the tsunami. So how to evaluate such kind of simulations? How to evaluate such kind of destruction? So we have developed such kind of simulators, the coupling simulators, Navier-Stokes equations. This is analysis for the FEM. And these are the physical experiment. The model scale is 1 to 20, and these are the concrete. And the water difference, the tsunami is coming here, and this is the port side. So the little bit water level differences pushed away such kind of breakwaters. So we reproduce these kind of phenomena by using the simulations. These are no sound, and this is the water level difference between the in front side and the rear side. Then push these kind of structures pushed away, so that such kind of destruction will be occurred. And here is the local side. This is a commercial area. And you can see that this is a little bit clearly inside the water. These kind of blocks are washed away. So that this is after the wash away, then such kind of simulation, such kind of phenomena, such kind of destruction will be occurred. So I think that these kind of tools can estimate how to destroy the tsunami and what size is needed to design. This is a bridge. It is almost same size. And these are the physical experiments. Okay, and this is the score before the behind the breakwaters. So these are the scoring will be occurred. So the water push the sound. This is the sound, and the score is occurred. And the last one is for evacuation, and maybe seven minutes or something. So in Japan now, to achieve the resilient society against a natural disaster, how to improve our security system or the secure system. So improve the resilient society system for the protection of life, property, and the industry, and the aim for the safe and reliability society. So that means we improve the prevention capacity. Sorry, I think it is better. Prevention capacity and prevention capacity and prediction capacity and response capacity. The response capacity is how to evacuate against the tsunamis. So, of course, the evacuation is depend on the human beings, but now we are using these kind of simulators. This is the propagation and the inundation and the evacuations. So this is connected with the multi-agent simulators by these kind of simulations. This is one example for the evacuations in the Chile tsunamis. So the black one is the people evacuated against the tsunamis. So the Chilean countries, the evacuation place is higher than the 30 meters. So the tsunami is coming, then people will run away to the higher point. And this axis shows the actual evacuation point. And this is the calculation evacuation point. So that means almost same evacuation place that they are choosing in Chile. And these are the actual evacuation distance, and these are the calculation evacuation distance. So they're almost same. These are the evacuation distance from the calculation point. So this is one of the good examination for the evacuation, and they are very good they are very good educational tools for the tsunami evacuations. And the last slide is how to evacuate from the tsunamis. This is the difference of the tsunamis evacuation and the case. This is 10 minutes after the seismic motion. Here is 10 minutes after. And these people evacuate when the 20 minutes after. So the 10 minutes after, the evacuation people can succeed to reach the evacuation buildings. But 20 minutes after, then maybe he hit. I think this is a tsunami, and these are the people, and the tsunami is coming. So this is the evacuation town, the evacuation walls, and he hit the tsunamis. So I think these kind of simulations can use the AWS simulations. So that I think these kind of simulations, if we can do it by using the AWS, then I think everybody all over the world can use such kind of simulations. That is a very good point to use the AWS cloud computers. Oh, okay, thank you very much. This is the last videos. How to... Yes, this is the this is the... Okay, I think you can understand. Okay, thank you very much.